Okay, another super quick intro. This one's going to be on the forces standard. And this one's not going to show all the details because it could be a little bit long. The first thing that we need to know is what is a vector. I'm not going to go over all the details. I'm going to tell you what you need to know. So we write a vector as A, AX, AY, AZ. Has components. That's a three-dimensional vector. It has units. If I have two vectors, B, which would be BX, BY, BZ, then I should be able to add vectors, A plus B. I cannot multiply vectors, but I could multiply a vector a scalar times a vector. You should be able to do that. You should be able to find the magnitude of a vector. Okay. You should be able to find the components of a vector. And that's just an example. That's not always true. Okay. So those are things we need to know about vectors because force is a vector. And so really we're looking at this case, F net, the total force equals 0. And 0 is a vector. 0 equals 0, 0, 0 newtons. There is one other thing that is important about forces. If I have two forces that are interacting, maybe gravitationally, and this is A and that's B, and they pull on each other, then the force of A pulling on B equals negative the force of B pulling on A. Forces come in pairs. There's always two, and they're equal in opposite directions. That's one of the important properties of forces. Okay, after that, we just have some special forces that we can use to talk about these things. Really, there's two types of forces. There are calculated forces and forces of constraint. So, calculated forces. These are ones where I can just get a value. So the first one we have is the real gravitational force. I will write it like this. So it's a vector. It depends on the masses of the two objects. G is a gravitational constant. This is a universal gravitational constant. And R is a vector from one planet to the other. And then that's R cubed, and that gives you the whole force. If you're on the surface of the Earth, we can write this as the weight. You could use W. And it's just mass times G, where G equals the vector 0, negative 9.8, 0 newtons per kilogram. And that's just an approximation to that form. There's also the electric force. F coulomb equals K Q1 Q2 R over the magnitude of R cubed. And you'll notice this is Q1 and Q2 are the electric charges. They interact, and it looks very similar to the gravitational force, and that's kind of important. There is also a kind of calculated force. I'm trying to see if I can remember them. It's both a calculated and a other type of force. But let's just put it with the other type. I think those are the main ones that we're going to see at first. But there are other calculated forces that we can use. So the next kind of force is a force of constraint. These are forces that can be whatever you want, and they're whatever you want to make something true. So my favorite example is this book on a table. If I have a book on a table, then the table pushes up on the book to make it stay stationary. So I have the gravitational force pulling down, and then this table pushing up, which we call the normal force because it's perpendicular to the table. These two are equal and opposite because it's at rest to make this true. Now if I push down on the book with my finger, I'm going to have another force pushing down, F finger. The book still stays at rest. So in order to make the book stay at rest, this normal force is going to have to increase. So the table pushes whatever needs to be done in order to keep that book where it's at, up to some breaking point. I mean, if I'm the Hulk and I push down super hard, the table breaks. It can't push up that hard. Okay, so N, we can't calculate N just saying there's a formula for N. There is no formula for N. Instead, N is a force of constraint. It does what it needs to do to keep that book where it's at. Another force of constraint is the tension. So let's say I have a ball and I pull with a string T1 that way and another string right here, T2, and then I have the gravitational force mg pulling down. These are strings, but I'm representing as vectors because the tension of the string is a force of constraint. It needs to do whatever it needs to do to keep that thing stationary. But there's one difference between the normal force. Strings only pull, and they only pull in the direction of the string. So if I have my string going this way, that's the way the force has to be. I know the direction. Okay, now there's one final force that's partially constrained, and that's frictional force. So we have a model for frictional force where the F friction, where the magnitude, I'll leave the vector off because it's just the magnitude, is less than or equal to some coefficient of static friction times the magnitude of the normal force. That tells me the magnitude of the static friction force for two surfaces rubbing together. Mu is a coefficient that depends on the two types of materials, and N is that magnitude of the normal force. The less than or equal to is because, let's say I have this, a box on a table, and I push with my finger, that's my finger, and it doesn't move. So I have mg and my finger, and then friction. If I push just a little bit and it doesn't move, the friction force has to be completely exactly equal to my finger to make it not move. It's not going to be the maximum amount, otherwise there would be a net force pushing this way and it would accelerate in the opposite direction I push. That's weird. Okay. So this is just a model for friction, but it's very useful. There's another frictional force, kinetic friction, and it's equal to a different coefficient, the coefficient of kinetic friction, that's the Greek letter mu, times the normal force, and it's if you're sliding and the two surfaces are moving relative to each other. Okay, that's a short introduction, but that'll help you keep everything organized.